Hello, how's it going, everyone? See some people chatting already before class even starts. All right, so I'm deviating a little bit from the schedule for this class. Let me just bring the schedule up, actually. So this was the schedule that we were sticking to, and as you can see here in the schedule for this course, today was supposed to be problem solving plus assignment 1. So what I realized is that what you need to know to actually do assignment 1 is in the 4th lecture. And just because of the randomness of how the term started, today being Thursday and that lecture being on a Tuesday, that's an extra 5 days that you won't really know what to do for the assignment. And so what I'm going to do today is I'm going to get started right away because I want to combine lecture 3 and lecture 4 and then go into assignment 1. So lecture 3 was pretty short, and lecture 4 is not that long either. And so I think that what we can do is we can actually combine both of these lectures and get A1 in as well. And so what that'll let me do is actually give you the 5 extra days for assignment 1 with you knowing what to do. So with that in mind, let me just jump right straight into it. So we're going to have a memeless class today. I'll get right straight into the lecture, and that way we can cover a lot more material. And this one may go a little bit long, but it's only going long because I'm taking a while to explain the assignment in full. And so if you have to go at the normal class end time, then that's fine. But if you don't, then stick around and you can ask questions and stuff about the assignment later. So let's get started. Alrighty, so as you can see, today's lecture is on probably the most important topics in the first half of the course. So this is introducing the notions of problem solving and search, and then lecture 4 was supposed to be search strategies, but I think we can fit them both into one lecture in order to give you extra time on the assignment. So we talked a little bit last time about agents and how the agents are solutions to problems. And we talked about rational agents, and rational agents are the ones that do the best thing given the information that they have. So rational agents maximize performance. In the simplest case, performance equals just satisfying a goal condition, okay? So satisfying a goal condition would mean something like solving a puzzle, reaching the end of a maze, beating the level, defeating your opponent, stuff like that, okay? So there's a goal condition and you meet it. And a problem-solving agent would be a type of goal-based agents. And so goal-based agent meaning that the agent is going to find a sequence of actions that satisfies the goal. So let's give an example scenario here, okay? So let's say we have a map of Newfoundland. If anyone from the course, this is Newfoundland, Canada. So if anyone in the chat or anyone watching is not from Newfoundland, this is where our university is located. So this is where Memorial University is located. And I see a bunch of questions in the chat, but I'm going to come back to questions once I get to a bit further into the lecture. So in this example problem, let's say that a tourist comes to Newfoundland, and of course they land in St. John's, where the airport is, and now the tourist wants to go to one of either St. Anthony or Snantney, if you're from Newfoundland, right? So St. Anthony is up here, or Port aux Basques down here, okay? So this is Port aux Basques. And so you're here in St. John's and you want to go to either one of those. So that's your goal condition. I want to be in either St. Anthony or Port aux Basques. And maybe that person says some extra constraints. So maybe they only have so many hours or however much time that they're in the province. And so that may impact where they want to go or what route that they take. Or maybe they only have a certain amount of money total for gas, okay? So we can have a goal in mind and an extra constraint in mind as well. So what is the goal then? How do we formulate the goal? So the goal is a set of states in the environment, okay? So here in our map, if we take states to be the location of the agent in the province, then a goal is a set of states in the environment that you would like to be in. So for example, this goal is an OR condition. I want to be in either St. Anthony or in Port aux Basques, okay? So that's one way to implement a goal. And this goal is going to be satisfied if one of those states is reached. And what do I mean by a state being reached? Well, if a sequence of actions leads us to a goal state, then the goal has been satisfied. Okay, so satisfying a goal means that the goal condition is met. And that means that the problem has been solved. So, the goal could also be an arbitrary function evaluation. So if we want to think about a goal in terms of like a more complex video game, well, we could have, well, if the enemy health is less than or equal to 0, or if I'm playing chess, then if the enemy is in checkmate, or if the player has all the pieces of the Triforce and Ganon is dead, right? So these are ways that we can form the goal. It's not always possible to form the goal as a set of discrete states like we are able to in this case, but it'll always be some sort of function evaluation that's possible. So, when we're defining this problem, and this part of the lecture is all about very specifically defining a problem, what do we need to consider? Well, what states are we going to consider in the province, right? So if you think about it, how are we going to chop up our environment? In this case, it's Newfoundland, right? So Newfoundland is actually a continuous environment. But as a computer, we can't represent continuous spaces, right? We have to chop things up into discrete spaces in order to apply, say, a graph or a tree search to that problem. And so which states do we consider? Well, for example, I could consider every square meter in Newfoundland, right? That might be a little bit too high resolution. If we consider that Newfoundland is what, 700 or 800 kilometers across? Can someone figure out exactly how wide Newfoundland is and put it in the chat for me? So if we have like thousands and thousands and thousands of grids in one direction and thousands in the other direction, this is like millions or billions of states, and that may be too many for our problem. But maybe we could try the towns in Newfoundland, right? So maybe each town is a possible state in our search. So if we're taking that as the states to consider, then what actions should we consider, okay? Well, in the first one, if we were considering every possible square meter in Newfoundland, then maybe one action was just like move left by a meter or move right by a meter, right? And so those actions, the resulting path would be so large that it would make our problem very, very hard to solve. So we could move from town X to town Y, right? Because every town in Newfoundland, well, every major town in Newfoundland is connected by a road, right? So we could have an action be move from St. John's to Placentia via the Trans-Canada Highway, right? That could be a possible action. So moving from town X to town Y, that could be an action in our search as well. And then what information is stored in a node for this search? Well, we could have, for example, the current town location, the time or distance driven so far, etc. All right. So, in a well-defined problem then, and this is a great exam question, I may tell you to define a problem very well for me. First, we need the initial state that the agent starts in. Second, we need the actions that are possible from each state. So this is, remember, it's the transition function or the successor function that we talked about last time. We also need the set of goal states that will tell us that our problem has been solved. So this may be a goal test function. We also need an action cost function. So how much do actions cost in our environment? And then the resulting path, so the sequence of actions, the path cost is going to equal the sum of the cost of the actions in the path, okay? So here's our example, the problem that we talked about at the beginning. The initial state is going to be St. John's. The actions are going to be moving between towns that are connected by a road, okay? So for example, moving between Clarenville and Trinity, or Gander and Clarenville, or Placentia and St. John's, etc. The goal is going to be, I want to be in either St. Anthony or Port aux Basques. And the action cost function for this particular problem is going to be the travel distance or the time or the money or something like that that you spend going from one place to another, right? So you actually have to factor in the cost when you're traveling somewhere, whether or not you want to, say, for example, be evaluating the time that it takes to get you somewhere, or the gas that it took you to get there, or maybe just the distance. Alrighty. So what's a problem solution then? When we talk about solutions, what does a solution for a well-defined problem look like? Well, a solution is going to be a path. So a path from a start state to a goal state. And a path, the definition of a path, is a ordered sequence of actions, okay? So for example, if I want to solve this maze, I go up, up, down, down, left, right, right? So that's an ordered sequence of actions. And it's called an ordered sequence of actions because the order in which you take the actions matters. The solution cost is then the path cost, okay? So usually this is the sum of the cost of the actions. In this case, it will be true. And in almost any problem that is a serious problem, the costs are all going to be greater than 0. Because when you talk about a cost, usually later on, we're going to be talking about minimizing the cost. And if the costs are 0 or negative, then you'd be able to repeat those actions at 0 or negative cost, and that doesn't really make any sense. So most problems assume that costs are greater than 0, and all of the problems in our course will make that assumption as well. All right, and that means that the optimal solution is going to have the lowest path cost among all possible solutions. So here we talked about solving a problem, right? So we have a solution. So a solution would get us from St. John's to Port aux Basques or St. Anthony, right? No matter what the path is. But the optimal solution would be the one that has the lowest path cost among all possible solutions. So for example, if we were talking about distance traveled, then we wouldn't be going around to a bunch of different unnecessary places in the optimal solution. But if you, for example, were a tourist and you wanted to see as much as Newfoundland as possible, maybe you would take the amount of towns visited as part of the cost. Or, as part of the cost. Okay, now, of course, we're not going to be looking at maps of Newfoundland all course, right? So what we are going to be looking at is graphs. And so hopefully you've all seen graphs before in courses. If you haven't seen a graph, let me know. But let's take this graph. Okay, so this graph, it's going to have states. All right, so states in the graph are represented by the vertices. So this is state A. Okay, this is a state. I am terrible at writing with the mouse. We have state A, state B, state C, D, and E. Here we have the costs. So the edges of this graph are labeled with the costs. So the edges define the legal actions in this graph. So here, this tells me that I can move from A to B with a cost of 6. I can move from A to D with a cost of 1. But I can't move from A to E, and I can't move from A to C because there's no edge connecting those vertices, okay? So, in this problem, the initial state is state A, the red one here. I apologize for anyone who's red-green colorblind. I didn't have that in mind when I made this. So state A is the initial state. The legal actions for this problem instance are moving from state A to state B is legal if there is an edge connecting them. Okay, so that's pretty intuitive. Also, we have the goal state, state C, over here that we're trying to reach. And the action cost function is the edge label. All right, so for example, the cost of going from A to B is equal to 6. Alrighty, so let's talk about the properties of this problem. Remember, we talked about properties of environments last time. This is a fully observable environment. It's static, okay? It's discrete, it's deterministic, it's single agent, and it's sequential. So this is the problem that we've defined, right? So all of these properties apply to it, and on an exam, I may give you a problem like this and ask you to list all the properties of the problem. So what's the objective though, right? What is the objective of this problem? Is it maybe we just want a path? So I want to get from A to C, and that's it. I just want to get from A to C. Maybe I want to have the shortest path possible. Maybe I want to have the path with the lowest cost, right? So in the chat, tell me the path or the solution that you would take to go from state A to state C in this problem. I just want to compare the solutions of people. And now, which algorithm do we use, right? So we don't know. We haven't talked about algorithms yet. So everyone is so far printing the same path, okay? And it'll be interesting which algorithms actually give us that path. So let's try search. And so we are going to apply the algorithmic technique of search in order to solve graph problems like this. Okay. So people in the chat seem to have caught on already that action cost matters, even though I didn't say that we were doing the cost optimal path yet. So what is search? All right, so at any given time that the agent is in its environment, it's going to have several available actions, right? It's going to be able to go up, down, from this node to this node, maybe jump or shoot a bullet or something like that. So the agent is always going to have several available actions. And the agent can explore various sequences of those actions. So we could say, let's try going left, left, up. Let's try going right, right, down. Or let's try going up, 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 right? So it's going to be able to explore various sequence of actions. And then it's going to evaluate all of those sequences and take the best one that it found within some performance measure. And that process of exploring an action and then evaluating the sequence of actions is called search. So, search will explore the problem state space, meaning that we are going to explore states of the environment, all right? Searching the space will generate what we call a search tree. And I'll give an example of this. And the search tree has nodes and it has edges. The nodes and edges of the search tree are different than the vertices and edges of the graph, okay? And I'll explain this difference now. So, let's talk about an abstract overview of the process of searching to find a solution to this problem. Okay, so again, we have the starting state A, and we're going to have our search tree represented over here on the left, all right? So, what we're going to do is we're going to form the root node of the search tree based on the initial state of the problem. And the initial state of the problem is A. And so over here, I have a node, and the state of that node is A. Now what I'm going to do is I'm going to expand this node. And what expanding the node means is that I consider all of the neighbors of this node in the original graph, okay? So, if I look at node A, and I want to generate its neighbors, then I'm going to see what the legal actions are from A. So from A, I can get down to D, and from A, I can get to B, all right? So I expand this node, the root node, by creating two more nodes with edges between them, okay? So here, we're looking at all the possible actions, all the possible first level actions in this search. And that is going from A to D and from A to B. All right, now what I do is I continuously expand nodes in the search tree. So let's say that I chose to expand D first, okay? And we'll talk later about how we choose to expand these nodes. So what nodes can I get to from D? Well, if I look over in my problem definition, I can get back to A, I can go to B, or I can go to E, right? So when I expand D, then, or the node containing D, then I can go to A, I can go to B, and I can go to E. Similarly, let's expand this node, right? So where can I go from B? Well, I can go A, I can go C, I can go D, I can go E. And so when I expand that, this is the process of expanding the search tree. And of course, I can keep going on and on and on. Each of these has a number of nodes that it can visit in the search tree, okay? So you can see over here that nodes in the search tree are different from the vertices in the graph. Why is that? Well, because, for example, you can see that in these nodes, we can be at the same state, right? So for example, here I went from A to D, and then I went from D back to A. But I'm down here in the search tree, right? So this concept is a little bit confusing right now. You will get used to it because we're going to be doing a lot of these examples, all right? So these are nodes in the search tree, and these are edges in the search tree. And these are vertices in the problem graph if we're looking at it that way. All right? So, and we're going to continue this process until the goal is found. Now, whether or not I found the goal here now, we'll talk about that in a second. So, one important thing to note is that the state space of this problem, meaning how many different states are there, right? A, B, C, D, E. The search space of the problem is finite. That means there are a finite amount of different states in this problem. But the search tree is infinite, right? Because there are infinitely many paths that we could take through this graph. We could go up, down, left, right, up, down, left, right, up, down, left, right, as many times as we want until we get to a solution, if we ever get to a solution, okay? So this over here is the search tree. This is the root node. It expands into child nodes, and we'll get into more of that in the future. So let's look at an example of search in a real problem, okay? So who out there has ever played the 15 puzzle before? I know this isn't, usually there's a 4x4 grid here, but I wanted it to be more clear, so I used the 8 puzzle example. But in this example of a puzzle, what we're doing is there are 9 spaces in this puzzle, and your actions at any given time are to move an adjacent square into a free square, okay? So my actions for this particular state of the puzzle are to move 8 to the right, 6 to the left, or 4 upwards, okay? And my goal in this puzzle, is this is a particular starting state, and this is my goal, is to arrange it so that, well, there's different people play it by different rules, but ideally, in this case, our goal is to have the blank square in the top left, and then to have 1, 2, 3, 4, 5, 6, 7, 8 in order from left to right, top to bottom in the square, okay? So, our actions that are legal are moving things into that empty space. So what would the search tree look like for this problem? Well, here's an example, okay? So we start at that state that we were looking at. Now, I know this is a little bit small, so bear with me. You can look at the slides later if you want. But the legal actions that we have from this state, we could move 7 to the right, we could move 6 downward, or we could move 5 to the left, okay? So this is the case where we move 7 to the right, and we can see here that 7 is now in that bottom slot. This would be the case where we move 6 downward, and now 6 is in the bottom slot, and the empty space is in the middle. Over here, we have moved 5 to the left, and now the empty space is in the right. And so what we do is we continuously expand with some search strategy, which we'll talk about later in the lecture, so that we find a path. Oops, I drew the wrong one. We find a path, which is a sequence of actions that actually leads us to a goal state. And in this particular example, they want you to fill it out in a circle, okay? So that is the process of search. You are taking a state, you're taking all the states, you create a search tree with some starting node, you expand it, so you take all the possible actions, you generate all the possible states, you create new nodes, and then from there you expand, you expand, you expand. So search is sort of an exhaustive process. You're searching all the possible sequences of actions until you find a goal. Okie doke. So let's talk about the search strategy. So what do I mean when I talk about search strategy? Well, here, for example, when we created the root node of the tree, we only had one node to expand, all right? And so it's obvious which node we should expand. It's the root node. It's the only one that we have. But after that, then we had this node with state D and this node with state B. Now we have to choose. Should we expand this node or should we expand that node? And the choice of which node to expand is called the search strategy, all right? So a lot of you out there are probably already thinking of things like breadth first search and depth first search, and we're actually going to go over them in this lecture, but in a way that hopefully none of you have seen before. Okay, so we're going to have a really nice unified view of search, and all of these algorithms it's going to turn out that all of these algorithms are almost identical. So breadth first search, depth first search, depth limited search, Dijkstra, all these algorithms are going to be almost identical. Okay, and that's really exciting to me, but we'll see how that turns out. Now, we saw that we have a search tree, right? So the search tree is this thing where we have a node and some edges, and then we have other nodes. But what information is actually stored in those nodes, right? We need to have some information in those nodes as sort of bookkeeping data in order to keep track of the search and do things like allow us to form a path, etc., etc. So the first thing we need in the node is the state. So for example, this node, when we arrived at this node in the search tree, we were visiting state A, or we were visiting St. John's, or we were visiting this particular configuration of the sliding tile puzzle. We need to store the parent node, right? So if we've generated a child node from a parent node, so if we're in the tree search, and we've expanded a node like this, then this is the parent and this is the child, okay? So if we expand a node, all of the nodes we could reach from that first node are the children of the parent node. So that's the tree node that generated this node, all right? Keep in mind, the parent node is not a state of the environment. It's a node in the search tree, and that's very important distinction. We may want to store the action. So this is the action, right? Maybe moving left or going up or going from A to B. That was the action that produced this node. We also want to store the path cost so far, okay? So the path cost so far from the starting node, or the root of the tree, to this node in the search. And that path cost is going to be called g of n. And you will be sick of hearing about g of n by the end of the lecture, don't worry. The depth of the search is different from the path cost. So the depth of the search in the tree is the number of actions that we have taken to get to this node, okay? So if we are at depth 2 in the search, it means that we have taken 2 actions to get there. Sometimes we refer to the root node as depth 0, and then the layer after the root node is depth 1, and then the one after that is depth 2. We could also store other data within these nodes that might be some optimization for a particular search algorithm. So for example, we could store some legal actions or heuristics, which we'll talk about next class, etc., etc. All right, so these are the things that we would want to store in the tree node. Alrighty. Okay, so I don't see any questions in the chat, so I'll keep going. And again, this is one of the more dense lectures because we're talking about a lot of definitions and we're introducing a lot of concepts. But some of these concepts I'm sure you've seen before, but hopefully this lecture kind of ties them all together in a way that you may not have seen before. And it will be super easy to remember all of these algorithms going forward for the rest of your life and you'll never forget them. All right, ideally. So again, There's a very important distinction between node and state. And I do not repeat this for no reason. People always have a little bit of trouble with this, so I'm going to repeat it again and write it down specifically. A state is a configuration of the environment. A node is a bookkeeping data structure that exists only within the search tree. And nodes are on paths within the search tree. And what do I mean by that? Okay, so here, these are nodes in the search tree. Okay, this node is on a path in the search tree. A path meaning a sequence of actions. So it happens to be on this path, right? This node is on this path in the search tree. These nodes contain other data that is not necessarily shown here. Over here, we have states of the environment. And this is an environment that we have drawn up, and we've drawn it as a graph, okay? So these are states of the environment. These are nodes in the tree. They are different things. They store different information. They mean completely different things. They just happen to look the same in this particular visualization. Okay, so here, let's say we're at a particular time in the search. So let's say we rewind to the search example that we did before. So we had root node A and we expanded it. And we expanded that into D and B, right? Then we took node D here and we expanded it into A, B, and E. So let's say we are at this particular configuration of the search tree. The nodes that we have expanded here, so the ones that we have generated all the legal actions from, we've colored in red. And all the other ones, the white ones, we are calling these leaf nodes, okay? So nodes that are colored in white here, these are leaf nodes. And this is also called, and these leaf nodes are nodes that have been generated. So we've generated the nodes in the search, but we have not yet expanded those nodes, okay? So we've put them into the tree, we have generated them, but we have not expanded them, right? And expanding means generating all the children of that node. And the set of all of the nodes that are leaf nodes is called the fringe, okay? So you can think about it. What does fringe mean? Fringe means like the fringe of a carpet is the edge of the carpet, right? So the fringe is the edge. So the edge of the graph is the leaf nodes. And so the collection of the leaf nodes is called the fringe. And the interior nodes that have children that are generated, those are not in the fringe. They are something else, which we'll talk about later. Okay, so now we get to our first algorithm. And just a note about these algorithms, if you go online and you search for this algorithm, you may not find it. This algorithm, General Uninformed Tree Search, I have named it this way because this is how it is named in the AI textbook, that the optional textbook that I put in the syllabus for the course, okay? So they call this algorithm General Uninformed Tree Search. And all of our search algorithms for the first whole half of the course, or maybe the first third of the course, will all be variants of this algorithm. All right, so our algorithm will be a function. We will call it tree search, right? Because that's what we're doing. We're searching a tree. As an input, it's going to be taking a problem, right? So that problem is like the legal actions, it's the states, it's all of that kind of stuff. And it's also going to be taking in a search strategy. And remember, the search strategy tells us which node we choose in the tree to expand. All right, and we'll get into search strategies, but just know for now that we need to have some strategy to choose which node in the fringe to expand. So, we're going to create the fringe. So the fringe is going to be some collection of nodes, all right? So that's storing the tree. The fringe initially is going to have the root node only. So that first node, node A that we talked about, we're going to create a node that is based on the initial state of the problem, right? So when we looked at the search node, that first one, this is the node that we put into the fringe first. Oh, I'm sorry, that was up too high. So when we create that first node, right, that first one, that root node, this is the one that gets put into the fringe to start. So at the very start, we create a new fringe. It's some collection, okay? And we put the starting node into the fringe. Now, we're going to say while true. So this algorithm is just a process that repeats forever, and then later we're going to have some condition that terminates it, okay? So the first thing we do is we say, hey, is the fringe empty? If the fringe is ever empty, then that means we have run out of places to search and we haven't found our goal. And so that means we can return fail, which means that we have not found a path to a solution, right? So think about that. If our fringe of unexplored nodes is empty, then we have nowhere left to search, so we return fail. Otherwise, if we have things to still explore, then we're going to choose a node from the fringe. And so that's going to come from our strategy. So we're going to say, hey, search strategy, select some node from the fringe to expand next, okay? If that node is the goal, right? So if the state of that node is the goal, then I can return my solution. I've found a path to the goal. That's awesome. So otherwise, if this new node is not the solution, then I want to expand that node with all of its legal actions to generate the child nodes and add that to the fringe. Okay? So this might be a really verbose way of looking at that general uninformed tree search, but it works, and it will become much easier to you to recognize once we start getting into specific algorithms. All right. Now, we said here, expand a node. What does that mean? So node expansion is the process of generating the child nodes in the search tree. So we have this function called expand, and we're going to have a node and a problem. We're going to have a set or a collection somehow of successor nodes. And then we just say, for each action in the legal actions from this node, generate a state, right, which is the result of doing action A at the state of the node. So this just says, for this node, take the state of this node, do all of the possible actions, and generate the resulting state. We're going to set the parent of S to the node, and then we're going to say the G cost, which is the path cost so far, is equal to the G cost of the node plus the action cost. All right, and we'll be doing examples of this, so don't worry. And then we set the action of the node equal to A, because that was the action that generated this. We set the depth of this node equal to the depth of the previous node plus 1. And then we add the successors to the set, okay, or to the collection. And then we return the successors. So this is really, really simple in concept. It's just when you write it down, it gets a little bit verbose, right? So let me go over here for a second. I've got my blackboard, all right? So again, this is the process of expanding. All right, so we've got a node. And essentially what that whole algorithm said was that for every legal action from this node, we generate a new node, right, with the new state, and we add it to the successor list, and then we return that successor list. So that's all we do, okay? Then if we were to expand this node, we generate all of its children, and we add that. And we keep the bookkeeping data structure. So for example, whatever the cost was to reach this node, then we add that to the cost of the action to reach this node. And that'll be much more obvious once I do the example later. So let's go back to PowerPoint. Okay, Now, all that stuff may have been a little hard to digest, but I just wanted to introduce that, and then later on in this lecture we get down into the details of it where it'll be really easy to understand. Okay, so now we have to talk about, before I get into the different algorithms, I want to introduce the concept of problem-solving performance. So how do we judge whether or not one algorithm is better than another algorithm for solving a particular problem? All right? There are 4 properties that we'll talk about, and we can compare all of the algorithms within those 4 properties. So those problems are A, completeness. So completeness means if it's complete, then it is guaranteed to find a solution if a solution exists. Okay, that's completeness. Optimality. Does it find the optimal solution? And the optimal solution again means the solution with the lowest cost sum. Time complexity. How long does it take to find a solution, right? So we always want to know about time complexity. We don't have infinite time, right? And also space complexity. So how much memory is needed to run the search? So time and space complexity are going to be measured on the size of the input problem or the input graph, okay? And the time is going to be measured in terms of the number of nodes generated. So the number of nodes generated in the search is going to determine our time complexity, and the amount of nodes that we have to store is our space complexity. And we don't talk about like how many seconds it took, right? Or how many hours it took to do the search. We're talking about the number of nodes that you had to generate. So the space is measured by how much memory is needed to store the maximum number of nodes, so the worst case needed at any given time. And so search and AI are traditionally going to measure the following when it comes to analyzing time and space complexity. So if you've done big O notation, right, hopefully you've done that before. Have people done big O notation? I think it's a requirement for this course. Can you type it in the chat if you have or haven't? All right, good. So the branching factor B, that's the maximum number of successors at any given node. The depth D of the shallowest goal node. Therefore, the tree size is going to be B to the power of D, okay? So just to look at that, I want to make sure this is clear for everyone, what these things mean. Let me go over to the blackboard. So if we have a search here, let's say at any given time we have 3 children, right? So pretend that all of these have 3 children, so all of these over here as well. So we're going to have a depth. So this is depth equals 0, depth equal 1, depth equal 2, depth equal 3. This here, the average number of nodes generated is B. This is the branching factor. So it's called B because it's the branching factor. And if we look at the tree, then the width of the tree is the branch, right? We talk about trees and branches. So if we take D, so for example here D equals 3, to the power of B, right? That will tell us how many nodes have been generated so far in that search. So here, for example, if we have generated all of the children up to this point, then we have D equals 2, so 2 to the power of B, which is 3, so that would be 8. Okay, so that's what this time complexity or space complexity is measuring. Okie doke. All right. What is heuristic search then? We will talk about heuristic search later, but I just want to mention what it is because it's a very important part of this course. It's an improvement upon uninformed tree search. So what we're going to do later is we're going to incorporate some knowledge into the search to inform it how to search better, okay? So for example, we're going to have really, really large search trees. How can we make the tree smaller? How can we choose a search strategy? How can we choose an action to perform? All of these are questions that we ask ourselves in heuristic search. and we're going to talk about data structures and other optimizations, etc. So what heuristic search will do is we will apply heuristics. So heuristics essentially mean guesses, right? Educated guesses. So we will apply heuristic guesses to the value of nodes, and then we will explore nodes in terms of the best heuristics, all right? And we'll talk about concepts like move ordering or iterative deepening. We'll talk about pruning nodes and bounding solutions, etc. So let's take a search example of a real problem and talk about like the space and the difficulty of this search, right? So let's talk about chess. We can apply search to chess, right? In chess, we have a certain state. So this is a state. We also have a certain number of actions that we can do at any given time, right? So these are the actions that a player can do. So chess, in a mid-game, about an average of about 40 moves at every possible state. Most of them, though, are really, really bad. Like, you probably wouldn't see anyone who is a good chess player like open with this pawn opening, right? And so if you talk to a chess player like Kasparov or Magnuson or Hikaru or anyone like that, they only look at a very small subset of the moves in the tree search at any given time. And so if we just did a naive tree search like we just talked about, we would have to search 40, then 40, then 40, then 40. But if we look at this, if we can get our search down to 2 moves per node, well, we save a lot of time, okay? So, for example, just looking 4 moves into the future with a branching factor of 40, we're already at millions of possible actions. But that would just be 16 if we had a branching factor of 2, okay? So if we're able to do heuristic search and prune branches really effectively, then what we can do is take our problem space and reduce it dramatically, all right? Okay, so just a recap of what we talked about so far. Problems are defined by the initial state, goal state, actions, and cost functions. The optimal solution has the lowest cost function among all the solutions. And search finds the solution by exploring the search tree. The search tree consists of nodes and edges, but nodes in the search tree are not states in the problem. It's a very important distinction. Problem-solving performance is measured by completeness, optimality, space, and time complexity. All right, so that's the first half of the lecture. That was supposed to be where we talk about assignment 1, if you looked at the course structure so far. But because you're going to have the video, I'm going to go a bit long, and I'm going to do the next lecture as well so that you can start the assignment right away. So me doing this, I'm rushing a little bit, but I'm giving you essentially 5 extra days on your assignment by spending an extra like 40 minutes during this lecture, right? So for the rest of the actual lecture time, we're going to go into the next lecture, which is search strategies, which is what I've sort of been teasing the whole time. And then after this, I'm going to be explaining assignment 1. So you probably want to stick around for that. The lecture is going to go a little bit late, but it'll be fun, right? Or you can watch the VOD later, and that's the great thing about doing things online, is that you don't have to be here live for that. So, search strategy. What is a search strategy? I've been saying this the whole time. So, uninformed or blind search is what we've been talking about so far. We have no information about the states or the problem description, right? All we know are that there's nodes. And so, hey, search algorithm, just go search these nodes. That's it. So we're limited only to our successor generation and our goal testing. So that means that I can expand nodes and I can test if they're the goal, but I have no information beyond that. If we were using heuristic search, we're not, but later on we will be doing heuristic search where we can guess which states are more promising and hopefully speed things up. But for now, the rest of this lecture, we will be doing uninformed search, okay? So, given that we don't know anything about the problem, what are the different algorithms, the different search strategies that we can use to explore the space? Okay, so the first one is breadth-first search. All right. Now, I know there's grad students out there who are saying, oh my God, why is he teaching us, breadth-first search? Or even the undergrads out there. Breadth-first search is a conceptually very, very simple algorithm, But what I'm going to do is tie all of these algorithms together in a really nice way. And then when we get later to heuristic search algorithms, you're going to see just how close they are to algorithms like breadth-first search. So, in breadth-first search, we expand the root node first, right? Then, the successors of the root node are expanded next. And then all of their successors are expanded next. So in general, what breadth-first search does, and we'll show an example of this, all nodes at a given depth are expanded before any nodes in the next depth. Okay? So we will expand every node at depth 0, then we will expand every node at depth 1, and then we will expand every node at depth 2 before we go any deeper. And this is going to use a queue for a fringe. Okay? And this will all make sense very, very soon. So this was the general uninformed tree search that we talked about earlier, right? So we have this fringe, which is the data structure, right, that holds our nodes. We just said that it's some collection, right? It's just some collection. To turn this algorithm into breadth-first search, and we'll show why this is the case, all you have to do is use a queue as your data structure for the fringe, okay? So, just look at the difference between these two algorithms. Okay? So, breadth-first search uses a queue, and if you don't know what a queue is, hopefully you do, you've taken that course. A queue is first in, first out, and I'll show an example of this. And then all we have to do is pop a node from the fringe. So this is breadth-first search, but it's almost identical to the general uninformed tree search. Okay, so let's look at an example of breadth-first search in action. Okay, so we're going to go back to this problem that we looked at before. A is the start, and C is the goal, right? So in breadth-first search, we have our starting state at the root of the tree. Then we are going to expand all of the children of the root node first. So we expand everything at the root node, and then we expand everything at depth 1. So we're going to expand D, and then we're going to expand B, right? And so then we're going to expand all of those children, then we're going to expand all of those children, right? So if we look at, let's say we're talking about a video game pathfinding system, right? This is what our assignment is going to look like. If we did breadth-first search in an environment like this, where I can move in 8 possible directions, okay? Then this would be my root node. This is my starting state. From here, I can go to these places, right? So breadth-first search will expand the first depth, which is just the root node. Then it will expand all of these. Then it will expand all of these, right? And here, the yellow nodes, those are the fringe, right? Those are the nodes that have been generated but have not been expanded yet. Once we expand them, they become red, and we get a new fringe of things. So breadth-first search looks like this. We are expanding the breadth of the fringe, all right? So, you all know that so far. Breadth-first search is not a new algorithm. But let's now analyze breadth-first search in terms of the 4 problem-solving performance measures, okay? Completeness, optimality, time complexity, and space complexity. So, optimality. BFS is complete. So in terms of completeness, BFS is good. Here, if I've written something in green, it means it's good. If I've written something in red, it means it's bad. Or it doesn't mean it's bad, it means we can do better. So, BFS explores the entire tree, right? If you think about it, it explores every single node in the search tree, eventually. And so it will find a goal. Eventually, it will solve our problem. It will find a goal. It will find, however, the shallowest goal node. So it will find the goal node at the shallowest depth, since it explores all nodes at a given depth before the next depth, okay? BFS, however, is not optimal. So, in general, it does not produce optimal solutions, since the shallowest node is not necessarily the optimal one, okay? So, breadth first search is optimal only if the path cost is a non-decreasing function in depth. What that means is breadth first search is optimal, typically. Typically the scenario is maybe all of our action costs are the same, right? So breadth first search, since it finds the shallowest node in the search, it's only optimal if all the action costs are the same, okay? Let's look at that example. So, here's the example. I've expanded all of this node with BFS. Then I expand all of D, okay? Then I expand all of B. And as I'm expanding, I find my goal. Boom, solution found. So what BFS will do, if we go back to the algorithm, okay, this is breadth first search, right? So what we'll do is it'll say, okay, I have some nodes in the fringe. I'm going to pop those off. If my node state is the goal, then return solution, right? So as soon as it finds it, it's going to find the solution. It's going to return the solution. So here, I've found this solution, right? But is this the optimal solution, right? No, it isn't. Because the cost of this solution is 11. It's 6 plus 5. So breadth first search, if you can see now, it will find the solution with the minimum number of actions. So that means it finds the solution, the shallowest solution in the search tree. But if we had kept looking and gone to the next depth, we would have found this path from A to D to E to C, okay, that has cost 7, right? Because if we look here, 1 plus 1 plus 5 is 7. So that is the optimal solution. But breadth first search did not find the optimal solution, okay? It found the shallowest solution. So that's one of the bad parts of BFS, is that you can find the optimal solution, but only if it is also the shallowest solution. All right. In terms of time complexity, BFS is bad, right? If each state has B children, and we consider that the goal is at depth D, then we have to search B times B times B equals O to the B to the power of D nodes generated, right? So back here, we have to search everything up until this node to find it. It's an exhaustive search. So it has O, B to the power of D nodes generated, which isn't very good. Also, BFS has horrible space complexity because we have to store the entire tree in memory, right? We have to store the entire tree. Brutal. So, the space is the number of nodes generated. So here's just an example of some of the breadth first search performance, okay? So, if we have a branching factor of size 10, right? Let's say we can do 10,000 nodes per second, and we have 1 kilobyte per node, right? So pretty typical problem. We can do 10,000 nodes a second. That's pretty fast. We have a kilobyte per node, and we have a branching factor of 10. Well, if we go down to depth 2, the number of nodes we've generated, right? So we've generated 10, 10, 10 because it starts at 0, right? We've generated 1,100 nodes. It's taken us 1/10 of a second, and we've used a megabyte of memory. Only by going to depth 4, we're already at 100,000 nodes, and it's 11 seconds, and we have 106 megabytes of memory, right? If we go to depth 10, we have 10 to the 11. Oh my god, what's that, like 100 billion nodes? It would have taken us 129 days, and we need 101 terabytes of RAM, okay? Who has 101 terabytes of RAM? I certainly don't. And so that you can see how even by just increasing the depth a little bit, this exponential time complexity. Like, we could leave something to run for 129 days, but we're not going to have 101 terabytes of RAM very soon. And then we go down to 14, and all of a sudden we're talking about like universe scale problems, right? Now, of course, there are supercomputers that can do this much faster if they have hundreds of thousands of processors, but an exabyte of RAM, you probably don't have that, right? So breadth first search, sure, it'll solve some small problems, but we want to avoid it if possible, okay? Now, let me just show you one other thing. So I want to go back to this breadth first search. Actually, no, I won't show you that now. I can show you that later. Okay, here's the next algorithm. We're going to talk about uniform cost search, okay, or UCS. So breadth first search is optimal when all action costs are equal because it expands the shallowest node, right? It's going to find, yeah, because it expands the shallowest node. Therefore, if all the costs are equal, then it's going to find the cheapest cost because the cheapest cost is going to be the shallowest one. Uniform cost search is going to be optimal for any cost. Okay, so let's modify breadth first search so that now it can be optimal for any possible cost. So UCS, unlike BFS, which is going to expand the first thing in the fringe, right, because we're using a queue, UCS is going to expand the node with the lowest path cost instead. All right, so if all costs are equal, UCS is equivalent to breadth first search, right? But it works only if all costs are greater than 0, and this is true of all these algorithms because we have infinite loops if we have 0 or negative costs, etc. And for a single goal, uniform cost search is actually equivalent to Dijkstra's algorithm. So this is really, really cool. So here is uniform cost search. Look at this. Look at how similar it is. We have literally just a generalized tree search, with the only difference being when we go to select a node to expand, we expand the node with the minimum G value. That's it. That's the only difference. So you can see now how this sort of unified structure for all of these algorithms makes things really, really easy. Because breadth first search and uniform cost search, the algorithms are almost identical. So in breadth first search, we would take the first thing in the fringe, okay? But here, we just take the minimum G value. I got a question, is this a heuristic? No, it's not a heuristic because a heuristic is a guess at how good something is. This is not a guess. This is the minimum G value. So that's, you're taking the node that is closest in terms of cost. We're taking the node that is on the shortest cost path so far, okay? Here's the uniform cost search complexity. Don't worry about this one too much. It's actually quite difficult to discuss and to prove, so I'm not going to be, you don't need to regurgitate this one for an exam. But it is complete if B is finite. It's optimal if all the costs are greater than 0. The time complexity is a little bit tricky, okay? It's measured by path cost, not by depth. We can't use B and D because we're not talking strictly about branch expansion. So here's the complexity, right? So there's the complexity. It's there if you need to know it. It's better than B. It's worse, sorry, it's much worse in the worst case than breadth first search. But the trade-off is that it gives us an optimal solution, okay? So that's a uniform cost search. So we've done breadth first search and uniform cost search. Now we're going to depth first search, all right? So the reason it's called depth first search is that it's going to expand the deepest node on the fringe. So breadth first search expanded the shallowest node on the fringe. Depth first search is just the opposite. It's going to expand the deepest node on the fringe. All right, so search goes immediately to the deepest level of the search tree to a leaf node, right? We're going immediately to the leaf nodes once they're generated. If a leaf is reached, it's discarded, and then we back up to the previous depth, okay? That's how you can sort of view depth-first search. And so, how are we going to turn this algorithm into depth-first search? Well, where breadth-first search used first in, first out, it used a queue, depth-first search is just going to use a stack, which is first in, last out, okay? Depth-first search is more often implemented in practice as a recursive function, but we'll talk about that later, okay? All right, so I'll get to questions in a second. So here is depth-first search. Depth-first search, we just use a stack for our fringe, okay? And whenever we go to select a node, we pop from the stack. So stack, it's coming from the end. Queue, it's coming from the beginning. So look now at the difference between depth-first search and breadth-first search. Here's depth-first search. Here's breadth-first search. So this is DFS. This is BFS. DFS, BFS. Okay? So these algorithms, which seem to operate in completely different ways, right, and have completely different algorithms, literally almost identical. Okay? It's just that in depth-first search, we take the deepest one, and in breadth-first search, we take the shallowest one. Okay. So, I want to show one more example of this. Okay, so let's look at, here we have the blackboard. So let's say that we have our fringe down here. Okay. So this is our fringe, and we're going to put nodes into the fringe. All right. So we have our first node. This is node 1. This is in the fringe. And the fringe is a queue for BFS. BFS equals a queue, right? So we put things into the queue, right? So here I'm going to generate some children. I'm going to generate 2, and then I put this one into the fringe, 2. I'm going to generate 3. I put it into the fringe. I'm going to generate 4. I put it into the fringe, right? Now, oh, sorry. When I did this a little bit wrong. When I generated this, I popped it from the queue, okay? So I remove it from that queue. Now, so pretend that one's not there anymore. When I then go to generate my next expansion, I'm going to choose the next thing in the queue. And of course, the queue is first in, first out. So now I'm going to choose this one. All right. So then I'm going to generate 5. I'm going to generate 6. And then I'm going to generate 7. Okay. Now, when I go to expand, I'm going to take the next one. And a queue is first in, first out. So we go from the start to the beginning. So I'm always taking the next one, right? Now let's look at what happens when I do DFS. Okay, so DFS equals a stack. Okay, now, so when I choose which node to expand, of course, I'm going to pop something off of the stack. And when you pop something off of the stack, that comes from the back of the stack, or the end of the stack, okay? So, here, I actually have to erase this in order for this to work. So, I'm going to choose, I suppose it'll be an eraser. All right, so I guess, oh, that's so odd. Give me a second. Out of practice. Okay, so we'll do it live. Gotta fix my chalkboard. Shouldn't be destroying it. Okay, so I've chosen this first one now to expand. So what I'm going to do is I'm going to expand. I need to change the color. So I'm expanding it here. Okay, so I generate node 2. I pop it onto the stack. right? I generate node 3, I push it onto the stack. I generate node 4, I push it onto the stack, okay? Now, DFS is popping from a stack when it chooses which one to generate next, right? So I'm going to pop off the last one because stacks pop off the end, all right? So here, I'm going to take 4 and expand it into 5, 6, and 7. So 5 comes down here, 6, and then 7. And now I'm going to choose the next one to expand. And so I'm actually going to choose 7, right? So you can see how using a stack turns BFS into DFS, right? Because I'm always going to choose the most recently generated thing, which is a leaf node, right, to expand first. So that is the difference between BFS and DFS and how it operates within the search algorithm and why they're so similar. So they do different things, but they're so simple. They're so similar in terms of their algorithm. Okay. So again, DFS uses a stack, BFS uses a queue. That's the only difference. Okay. Now, if you ever want to implement DFS in the wild, you'll probably be implementing it recursively. Okay. So here, just so you know, in this course, we're going to be implementing it as the generalized tree search. But here's how you would put in DFS as a recursive algorithm. You have a function, DFS, right? So if first in our recursive algorithm, we check, hey, is the state of the node equal to the goal? If it is, return the solution. Otherwise, we generate the successors of the node, and then for each of the successors, we call depth first search on the problem, right? And then somewhere outside, we call depth first search on the root node with the problem. So this is a recursive function. This is probably how you've seen depth first search implemented before. That's it, okay? So this is a recursive implementation of depth first search, and it works well, but looking at it in this way doesn't show the similarity to breadth first search. Okie dokie. Depth first search is performance. In general, DFS is not complete, okay? So we can enter an infinite loop really, really easily in depth first search. So for example, depth first search can just go back and forth between like, I'm gonna go from A to B to A to B to A to B to A to B. And that's not cool. So enhancements can sort of make it complete, but we're not gonna talk about those right now. DFS is also not optimal. It can return the first goal found, but that could be anywhere in the tree. So it's not complete and it's not optimal. Right? That's terrible. It's not guaranteed to find a solution, and even if it luckily does find a solution, that's not going to be the best solution. Its time complexity is bad. So it may go down infinitely long paths. So if M is the max depth of a solution node, then possibly our worst case time complexity is B to the power of M. It's way worse than B to the power of D, where D is the first solution, okay? Its time complexity is horrendous, but its space complexity is awesome, right? Because we're only storing this one path down the tree. So it's B times M, not B to the power of M. And if I go back, no, I won't go back now, but it's B times M because it only has to store the current path at any time. So it uses B times M memory instead of B to the power of M memory. If we want to see how depth first search works in practice, a lot of maze solving algorithms are implemented as DFS variants, okay? So here we are basically going down a node until we reach a point we can't go anymore and then moving back, right? So this is what depth first search is going to look like, but it's not necessarily going to give us the correct path. All right, so I'm just waiting for this to finish. and it's going to back up and find the solution eventually, right? So that's how DFS would find a goal. Okay, next algorithm. I got a couple of questions here. Wouldn't it be easier to refer to stacks vertically? Yeah, I guess so. I just didn't draw it that way. Apologies. In a stack, you pop the last thing in the stack instead of first. Yep. No. Taking the smallest cost is not a heuristic. We'll see why that is once we get into heuristics, but heuristics are guesses, okay? They are estimations of which thing is best. Taking the lowest G cost, the G cost is definite, right? It is the path cost so far. And so these are search strategies. These are ways in which we guide the search using only the information that we know for sure. Heuristics are when we cut things off based on guesses. All right, so that's all the questions so far. Now, depth-limited search. And I said at the beginning of this lecture that it's going to go a bit long. We're already at like the official time, but I want to get through this, and I also want to give you the assignment because the assignment is like bonus. It's bonus lecture time. I'm going to go over all the assignment in this lecture so you have it all in one video that you can watch back. So, depth-limited search is also a very interesting concept. In what we saw before is that depth-first search can go like A, B, A, B, A, B. It can go down the right-hand side of the tree and it can just get lost, right? It doesn't know where to go. So how can we prevent depth-first search from getting lost? Well, we're going to apply a depth limit to the search, and we'll call that depth limit L. So we're going to enforce that nodes at depth L have no successors. And what that means is if we've reached depth L, we just stop there. So it solves the infinite path problem because it will search the entire tree only up the depth L. But it introduces a new problem. It's incomplete if the search depth is bigger than L, right? So if we've said stop at depth 3, but the search is at depth 4 or higher, then depth-limited search can no longer find a problem. It has now the same time complexity as BFS, right? So it's B to the power of L. So that's better than depth-first search. And its space complexity is also really good, right? Because we don't need to store the whole tree at the same time. We only store the path that we're on. So here's an example of recursive depth-limited search. All we have to do to turn depth-limited search, or sorry, depth-first search into depth-limited search is impose one more constraint. And that just says if the depth of the node is greater than L, then just stop. Okay? So that's all I have to do now for depth-limited search. But who in the chat can tell me what the problem with this is? Oh, never mind. I just told you what the problem with is. Here's the problem. The problem is that we don't find a solution if the depth is greater than the limit that we've set, right? So how do we choose the limit so that we know we will find a solution no matter what depth it's at? So when we choose a maximum depth, we have to do some sort of analysis of the maximum possible path length. This is also known as the diameter of the search space. And it's also... Oh, sorry. That was incorrect. How do we choose the maximum depth? All right, how do we choose that value of L? Well, there's a number of different ways that we could choose it, right? Let's talk about some guesses. So let's talk about, like, we could analyze the problem. And maybe if there's so many states, maybe we know that there's 5 states, so maybe the maximum path length is 5 or something like that, right? Maybe our search length has like a certain diameter, so I could measure it and say, well, the length is going to be at most this amount of things. Or maybe it's equal to the number of states in the problem, but for some problem that's really big. But we don't want to make those guesses. Let's let the search figure it out. So here is another algorithm. It's called Iterative Deepening Dfs. And what does that mean? So what we're going to do is we're just going to gradually increase the depth limit. So we'll do a depth limited search for depth 1, then we'll do it for depth 2, then we'll do it for depth 3, and we'll do it all the way up to depth m until we find a solution. So this means that the goal will eventually be found at the shallowest depth, right? Because we're going depth 1, depth 2, depth 3, depth 4, depth 5. Oh, if the solution was at depth 5, we'll find it and we'll return it then. And we know no solution will have been found up to depth 5, because if there was a solution at depth 4, we would have found it when we searched to depth 4. So this means that Iterative Deepening DFS has the same completeness and optimality as BFS, because it's guaranteed to find a solution, and it will find the shallowest solution, which is optimal if and only if the action costs are the same. Okay? But it has the space complexity of breadth first search, or of depth first search. So we've taken the completeness and optimality of breadth first search, and we've got the space complexity of depth first search. So this is like win-win-win, right? But there's a little bit of a catch, and that is the time complexity of iterative deepening depth first search, right? So if we think about it, it might seem a little bit wasteful, because what we're doing is we're searching first to depth 1, right? So we search these 3 nodes. Then we discard, if we didn't find a solution, we discard all of that, and then we search everything up to depth 2. And if we didn't find a solution, we search everything up to depth 3. But when we search up to depth 3, we also have to search everything up to depth 2, right? And so every time we do a new depth, we research everything that we've searched before. But fortunately, the amortized time complexity of this, we're only searching about double the amount of nodes that BFS would have searched. And why is that? Well, I'll show you. The number of nodes searched at depth 1 is d times b, right? Because there's only one instance of the branching factor. At depth 2, we have b squared nodes. At depth 3, we have b cubed nodes. Up to depth d, we have b to the power of d. And we know from our time complexity analysis course that whenever something is exponential like this or quadratic, we take the maximum factor. And so the time complexity is the same as BFS. The space complexity is the same as DFS. But in practice, even though the time complexity is the same, it generates about twice the amount of nodes. Okay? And the reason for that is the following. If we look here at depth 1, we have twice the amount of nodes, or we have one more node than the previous depth. So we had 1, now we have 2. At depth 3, we have 4 nodes. 4 is equal to 1, 2, 3 plus 1. Down here we have 8 nodes. 8 is equal to 4 plus 3 plus, 4 plus 2 plus 1 plus 1. The next one, we have 16, which is equal to 8 plus 4 plus 3, or 4 plus 2 plus 1. So in practice, we search twice the nodes as BFS. Can we set the last depth searched as the starting point to reduce the time complexity? No, we can't. We always have to start from the root node, because we had to have all of that information of the path costs so far, okay? So we do have to come back down in general. When we talk about optimizations later, there are some things we can kind of do, but no, we have to search all of it. So in general, iterative deepening depth first search is preferable to breadth first search because it has all the same properties, except it has a better space complexity. Okie doke. So this is recursive depth limited search, all right? We talked about this before. So assignment 1 for the undergrad students is just breadth first search and depth first search, but for 6980, the grad students, you're going to have to do iterative deepening depth first search, all right? So you have to pay attention to this one more so than the undergrad students. So let's talk about recursive depth limited search. We've got a couple of other parameters here. So what we do first is we're going to say that was there a cutoff, okay? So a cutoff means that did we cut off at a given depth or a given depth limit L. So the first thing we check in our recursion is if the state of the node is the goal, return solution. Otherwise, have we gotten to the depth limit L? If we have, we just return that a cutoff happened, okay? Otherwise, for every state in the expansion of the problem, we recurse on DSL or DLS. Now, if the result was a cutoff, then we say a cutoff occurred. We mark that down. Otherwise, if the result is not equal to a fail, we return the result, okay? Then what happens is when we're outside of this expansion, meaning we haven't found a solution yet, if a cutoff occurred, then we just return cutoff. Otherwise, there's nothing left to search, so we return failure, okay? So all this does is it says, I'm going to search everything up to depth L. If I got a cutoff because I hit the depth L, mark it as such, or if no cutoff occurred, then I've actually failed and I can't find a solution. So what does iterative deepening then look like? Well, it looks like this. Iterative deepening depth first search is the algorithm. So for D from 1 to infinity, we have a result which is equal to, hey, call the depth limited search for the node at a certain depth D. If the result is not equal to cutoff, then this means that we just have the result. So if the result was failure, then we can't find it. If the result was a path, then we did find it. Okay, so that's iterative deepening depth first search. So if we compare our search strategies, what we have is the following. So if it's green, it means that is something that we want. If it's not, it means it's something that we don't want. So if we look at iterative deepening depth first search, then yes, it has a good completeness. It is complete, meaning that if a solution exists, it will find it. It is optimal if all costs are equal, but in general, it is not optimal, okay? It has O to the B of the power, B to the D time complexity. That's not great, but it's kind of the best we can do up to now. And it has a B times D space complexity, which is the best we can do right now, okay? Now, just going forward with the rest of this lecture, and again, this has gone 15 minutes over already, but I'm just recording this, right? So we can get away with not having this lecture in another class, which is great. So just some terminology going forward, okay? The algorithmic terminology and the names are from the textbook, okay? So the names aren't necessarily important. And when I talk about the names, I mean tree search versus graph search, which we'll talk about in a second. So just know that the reason I'm calling them this is because it's from the textbook. And if you're following the textbook, I want you to be able to follow along. So here's a really, really, really important concept. Avoiding repeated states, okay? So this is one of the most important search ideas, especially important with reversible actions. Reversible actions meaning I can go to the right and then I can come back, or I can go right, left, right, left, right, left. If that happens, I can very easily enter an infinite loop in my search, and I don't want to do that. So most infinite loops and wasted time can be avoided simply by not returning to identical states, okay? So what we can do is we can just remember states that we've expanded and not re-expand. And this can lead to exponential savings in the number of nodes generated. Excuse me. Alrighty. So we're going to introduce the concept of a closed list. So a closed list is a data structure, and this is just a collection of states that we have already expanded. And so the closed list stores expanded states. Sometimes this is implemented as a hash table or a dictionary or an array for efficient lookup. And what we're going to do is we're going to check if the state of a node is in the closed list before we expand it. And so now, because we have this thing called the closed list, we are now going to turn the fringe into the open list. Okay? So what we called the fringe before is now going to be called, from here on, the open list. So the open list is the fringe of unexpanded nodes, and this is often implemented as a priority queue, and we'll talk about that later. Okay, so this is the general tree search algorithm that we looked at already. Remember, except now we call the fringe, what was the fringe is now the open list. Okay, so what we're doing is this is a new algorithmic introduction, and we're introducing the closed list. And the closed list is going to store states that we've already expanded, right? So we don't re-expand them. And so what does that look like? Well, it's a very small change to this algorithm. It's a very small addition, okay? Here it is. So here's what we knew, and here's the new thing. So, this was the tree search algorithm. Now we have something called graph search, okay? It's only called graph search because that's what the book calls it. But it's still a tree search algorithm, okay? So it's called graph search because the book has the algorithms with the closed list is called graph search. So the additions that we've made is we've added a new data structure, which is the closed list. So now we have an open list and a closed list. And we make one more addition down here. What we do is, so in the while loop, well, first of all, we say, okay, if the open list if it has nothing in it anymore, then we can't search, so we return fail. Then we select a node from the open list to expand next. Then we say, if that node is the goal, then we return a solution. But now we have one more step before we expand, okay? So normally we would have gone right to the expansion step, but what we're going to do is the following. If the state of that node is in the closed list, continue. And what that means is, if the state of this node has already been expanded, then don't expand this node anymore, okay? So once that is done, if it's not in the closed list, then we are about to expand this node, so we add this one to the closed list, all right? Then we do as normal, and we add it to the open list. Okay, so the closed list, again, it's just a list of states that we've expanded so far, and all we have to do is check every time before we generate the children of a node, has this state already been expanded? If it has, then don't expand it again. So here is what this looks like. It's just 3 extra lines of code from the previous search algorithm. Okie doke. So a couple of notes about it. Again, it's only called graph search because that is the name of it in the AI textbook, okay? It is still an algorithm that searches a search tree. It just uses the closed list to avoid repeating searching of nodes that represent the same environment state. Okay. So, for assignment 1, you will be implementing breadth first search and depth first search using open and closed lists. Okay? So this is literally the solution to assignment 1. That is the code you have to implement for assignment 1. Now, I'll tell you later why this is not literally the solution, because you have to implement it into a particular framework. Here's breadth first search. Look at the difference. Again, it is one line. It's one word different. You go from a stack to a queue. Okay? So BFS is a queue, DFS is a stack. So what is the difference between tree search and graph search? Tree search will remember nothing. Remember, it just keeps it can go back and forth between nodes. Graph search will remember states that it has expanded before. All right, so it will never re-expand a state a second time. Tree, graph search, just the name, but here is the actual difference between them. Okay, just to let you know, okay, the graph search complexity, its time complexity is far better than the general tree search because we're only ever going to generate a number of nodes that is equal to the number of states in the environment. which in most cases is far fewer than b to the d. The space complexity is also far better, right? It has to store all the states in memory in the worst case. But the number of states is far fewer than b to the d, and so it's way better than breadth first search, but it's not better than depth first search. But here's the thing. Graph search may no longer be optimal, okay? It's kind of tricky. It depends on each underlying strategy, so we won't go into it. But graph search keeps the original path and discards new paths as they're found, which may or may not be optimal, okay? So it's only optimal if we can guarantee that the first solution found is the optimal one. So if your only goal is to find a solution, then you use graph search. If your goal is to find the optimal solution, then you have to make sure that like BFS or UCS is the thing that you use, because this will only return the first solution found. Okay, I'm going to leave this bonus enhancement in the slides, but I'm not going to explain it right now. Okay, that's there if you want it for the assignment. That's a bonus enhancement. Okay, now that's the lecture. I know I went how far over time? 20 minutes over, okay? So that is like the lecture part of this stream. But now I'm going to explain the assignment. And I know I'm late, but by doing this instead of next Tuesday, you get 5 extra days for the assignment, okay? Alrighty then. So let me really quickly pull up, and I'll answer any questions as well while I'm explaining the assignment. I just have to pull up the assignment. Open with Google Chrome. Okay. Okie dokie. Here is the assignment. So, the assignment, and okay, assignment starts now if you're watching the VOD, right? Here's the timestamp for the assignment. The assignment is going to be an environment that I give you. So this looks complicated. All this code is written for you already, right? So what you can do in here is you can select a number of different things and you can see pathfinding happening in real time. So here you can choose a different algorithm. So the solution comes with the assignment, all right? But the solution is obfuscated, and I'll talk about that in a bit. So if I'm looking at pathfinding, what I can do is, well, first of all, let's look at the the assignment due date is listed. So for example here, let me switch the scene, okay? So the assignment is being given out today, and it is, no, it doesn't mean you're getting 5 more days. It means you get the full 12 days, okay? So this is probably by far the easiest assignment. It's just implementing BFS and DFS, okay? So you get the 12 days to work on this assignment. The grad students have a little bit more work to do, but I'll get into that. So it's given out today. You get till the 29th to do it. Okay. So let's go back. Actually, I can just pull this over here. There we go. Okay. So let's read the search visualization instructions. So I can left click and drag to set a beginning and an end. So I'm left clicking the mouse and I am finding the shortest path from one place to another in the environment. In this environment, paths are possible within, let me just go the path only. Paths are possible within the same color of the environment, okay? So this just means that I can pathfind within the green, but I can't make a path from within the green to outside the green, okay? I can pathfind within the blue, but I can't make a path from the blue to the gray or from the blue to the green. Now, I've made it look like an environment, but really these are just colors. They don't really mean anything, okay? Also, I can't pathfind from this blue to this blue because there's another color in the way. So a legal path in this environment is one which goes entirely through the same color. All right? So this is the solution code. And what you're seeing here is, if I drag a path like this, all of the red nodes are in the closed list. Okay? So those are states that have been expanded. All of the states that are in yellow, their nodes are in the open list, right? Now, what I can also do here is I can click and click a start and an end, and then I can show animated search, okay? So the animated search will actually run the search in real time. So this is showing you how the search actually operates. So the yellow is the open list, or the fringe, and the red is the closed list, okay? And once the fringe, or once the closed list reaches the goal, that is when your solution is found, okay? Now, I can choose from a number of different maps here as well, okay? So I have like some caves here, and I can just click and drag within these caves. I can load up a Starcraft map, which is like, I can toggle on or off the grid if I want to. So this is a Starcraft map, which you can see it's lagging a little bit more. Here you can see how much time is actually being spent generating each path, right? So for example, this path took 20 milliseconds to generate. Okay. Here, I have a very, very simple L-shaped grid. And if I show you this animated, then you can see how this is actually running, okay? So this is how the search actually happens. That's how BFS actually happens. If I check DFS, it's really bad, right? So DFS is going to find a solution, but it's going to be a terrible, terrible solution. Breadth first search, since I'm only moving up, down, left, and right, then there's no heuristic or anything in this assignment, okay? This is just uninformed tree search. And this assignment is just to get you used to the assignment structure, because this assignment structure will be used for all the assignments for the rest of the course, okay? The exact same structure. So, what did we say before about optimal paths? Well, I said that if all action costs are the same, then BFS will produce an optimal path. And since up, down, left, and right all have the same cost, right? They all travel the same distance, then breadth first search will give you the optimal path if you use up, down, left, and right, okay? Optimal meaning the least path cost. So whenever you do a path, over here, you can see a bunch of stats, okay? So you can see the start node and the goal node. This is the X and Y value. You can see the total cost of that path, and it says 10,400. Well, every path cost, every action cost of moving up, down, left, or right, I've given that a cost of 100, okay? And when we go into diagonals in the next assignment, we'll see why I've given this a cost of 100. But every action is a cost of 100. So here, if you see 10,400, that means the path cost is 104 actions, essentially. There were 1,400 nodes in the closed list. The amount of time it took to generate this path was 6 milliseconds, and that works out to 245,000 nodes per second searched. Now, don't worry if yours does not run as fast as mine. My solution here has a lot of optimizations in it that yours will not for this assignment, okay? All right. So, the other good thing about this assignment, if I just reload the page, is, oh yeah, and by default, there is something happening here for the student. So if you select student DFS, student ID DFS, student BFS, right now it just returns this obviously illegal path. And it's your job as the student, when doing this assignment, to fix that so it's actually generating the correct path, okay? So, the really cool thing about this is that you are going to know, as students, as soon as you've gotten 90% in this assignment, okay? because there's a button here that says Run Tests. And the Run Tests button is going to compare your code to the solution code and print out whether or not you got it correct. So up here, for example, if I click the solution and click Run Tests, you can see here that all of them are green. I've gotten 20 out of 20 of them correct, okay? So what it does is it runs the path. It has 20 built-in cases. It runs a path in the solution, figures the path cost, and times it, and then it runs your solution, or your code, and figures the path cost and times it. So what it does here is it runs all of those. So for example, again, if I choose student BFS, it's going to time all of those out. Now, you only have to worry about the tests for BFS, because DFS is not optimal, okay? If you can see here, all of the DFS tests fail. That is completely fine. That's completely fine. All right. So that is how you can test your code. You start with 7 out of 20 correct, but you do not get 7 out of 20 marks if you hand in this, because your code obviously does nothing, right? So if you hand in the code that's given to you, you're still getting a 0. So, okay, so that's what the assignment does. Now, here's this. This assignment does take a while to explain. It's probably going to take me about 30 minutes to explain the assignment. And I know this has gone like way over time already, but you're going to appreciate having this as a VOD, because in previous courses, all they had was the in-class explanation, okay? So you're going to have the VOD to refer to, and yes, the legal actions are only 4 directional cardinal actions. So up, down, left, and right. Okay, so that's what the path is. Now, let's get into the assignment itself. So you are going to be given a zip file containing the following files. Okay, so I know this is extremely small, so I'm going to open it up in VS Code. Okay. I highly recommend Visual Studio Code for JavaScript editing in Windows. It's a great editor. I use it all the time. I love it for JavaScript. So, for those of you who are new to JavaScript, I'm going to post like literally any intro to JavaScript code is going to be fine for this course. It looks a lot like Java, behaves a lot like Java, but here's how this assignment is structured. First of all, you get a complete marking scheme for the assignment, okay? So you know exactly how many marks you're going to get on every assignment, because I give you exactly how much everything is worth, okay? So there's no guesswork in this assignment. So we have points for style and code, and whether you removed the comments or functions used were appropriate, blah, blah, blah. Tell you about the data structures, the other functions, all the pathfinding, all the test pass, etc. All this is there for you, so you know exactly what you're going to get on the assignment. Okay, now, the way JavaScript works is that you have an HTML file. Okay, so all the JavaScript is going to run within the browser. The HTML file is here. It's set up for you. And if you're not used to JavaScript, this is the assignment where you sort of get used to JavaScript, right? How it works. So the way that JavaScript is imported into the browser is that in your main HTML file, so we have index.html here, you are going to use the script command here to import the JavaScript. So it's importing all of the different JavaScript files, and this is where your code is going to run. I've architected this in a way such that you do not have to worry about any of this architecture, and we'll get to that, and I'll explain why. So this here, this you don't need to worry about. This is just how I style the HTML file, so this is all CSS. This is how the JavaScript gets run for the first time. So if I go back to the file here, the way that this actually works is that this is an application written in HTML5 canvas that refreshes 60 times per second, okay? That's very important to know. So this is being called 60 times per second. So whenever I generate a path, it's drawing that 60 times per second. So if I go here and I do the animated search, the reason that this is animated is because it's calling your search iteration function every 60th of a second, or every 16 milliseconds. And then it's animating that as it goes. That's how the animation is done. So if I go back here, this just sets up the code. So I have code here for setting up the GUI. You do not need to know how the code for the GUI works. But I will go over it just so you have it, okay? Then I'm going to set up the main loop. So essentially this just says call the update function every 1,000 divided by 60, so that's 1,000 milliseconds divided by 60, so it's 60 frames per second. The update function of the GUI is called. And then I have a function, update, and then it is drawn once every 60 seconds, okay? Now down here, you see a whole bunch of nonsense. This is how the maps are included, okay? So if I go back here and I select different maps, okay, they are actually included in the HTML file, and the way that they are encoded is just as 2D arrays, okay? They are 2D arrays of integers, and the integers just correspond to a given color, all right? So for example, in the default map, it's 00000. So if we go back to the default map, 0 corresponds to a gray tile, and then green corresponds to a 1, and then 2 corresponds to a blue. So, did I type all of those numbers? I used a program to generate them. Actually, I painted them and then outputted the bitmap to a text file. So, that's how the maps are there. Next, we have 3 files relating to the GUI, okay? We have a grid. Now, a grid is a data structure that stores the map itself. You need to know how this in particular works. So grid is going to have 2 functions that you have to worry about. It has get, so it has get xy. So if you call grid.getXy, so for example here, this is position. In the bottom left here, you can see the position. So this is position x equals 13, y equals 61. So if you call map.get 1361, you will get back the integer value of this map, okay? And why do you need to know that? You need to know that because you have to program the legal action generation for the states in this map. And the legal action generation essentially says, I can only move between states which have the same color. Okay, so from this place on the map, I can move up, I can move left, I can move down, but I can't move to the right. And the way I can tell that programmatically is that if I say map.get 10.7, if that is equal to map.get 11.7, then I can get to that. That's a legal action. I can move to the right. But here this is going to have a value of 2, and this is going to have a value of 0, because 0 is equal to gray and 2 is equal to blue. Okay, so that's how I do the legal action generation. Okay. And then another function is out of bounds, all right? So this function essentially says, is the input x and y value, is it off the map, right? So this map is 16 by 16. So if one of those x or y values is either less than 0 or greater than 16, then that's not in bounds. So it is out of bounds. So is OOB will tell you if it's out of bounds. Okie dokie. So then there are two JavaScript classes which do all the setting up of the user interface. You do not need to worry about that. Okay? The user interface is not your problem. This is what I've set up. I've done a lot of work setting this up, so I hope it's a little bit appreciated. Okay. Someone asked, can you pathfind in gray? The color doesn't matter. The rule is you can pathfind only within the same color. So you can pathfind all you want as long as it's all within the same color, whether that color is green or blue or gray. So for example, I can pathfind within the green, I can pathfind within the blue, I can pathfind within the gray, but I can't go from one color to another. Okay? Now, there are two other files. One is my solution code, which I have obfuscated pretty well. Okay? So this is the solution code. Now is when I have to give the speech about cheating. Okay? Do not attempt to de-obfuscate this solution code. There are websites out there that will try to de-obfuscate this solution code. I have used all of them. If you hand in code that is de-obfuscated of my code, I will know the exact website that you use to try and de-obfuscate it. Not only that, but I have made a bunch of optimizations in here, and it uses a completely different structure than your solution code uses. So even if you could perfectly disassemble this, if you use that as your solution, I will know, and it will be very, very punished. Okay. This is the solution code that is not obfuscated that I won't show. Here is your code. Okay? So, the way that this works is the following. You have this class, which is called Search Student. This is the class that you will be writing all of your code in. And in fact, you will only be submitting this file when you submit it on D2L. Okay? So, up here, you see Search Student, Computer Science 3200 Assignment 1. You will write the names of all of the students in the group here under Authors. So all of the students, if you're solo, just write your own name. If there's two people in the group, write both names. Only one person from each group is submitting an assignment. So let me read this now. All of your assignment 1 code should be in this file. It is the only file submitted. You may create additional functions or member variables within the class, but do not rename any of the existing class variables or function names, since they are used by the GUI to perform specific functions. Okay? So, inside this class, Search Student, there are a number of functions, and I have very well documented all of these. Okay? So, let's go through this together. It looks extremely complicated. If you're a third-year student, this is probably the most complicated assignment you've had so far, but that's why the first assignment is just implementing BFS and DFS, okay? So the algorithm is simple, but it's the first time you've seen this code. Therefore, the architecture is the thing you have to wrap your head around in this assignment. But it's not that bad, trust me. So, let's go through all the things that are in this assignment. So, first of all, the constructor of the search student. So in JavaScript, this is how you have the constructor of a class. The parameters, the input variables to this constructor are the grid. So the grid, again, is the map that you will be using, okay? So that contains all the data of the map. Then there's also a config. So the config is specified by these things that you choose here, okay? So the big thing here is whether or not it's going to be the BFS, the DFS, or the IDDFS algorithm. And again, IDDFS is only to be implemented by the graduate students. So that's what the config is. It's going to hold the actions, it's going to hold the action costs, and it's going to hold the strategy. All right. So what I do is I have the grid. So the this.grid, that's the variable that holds the grid. Okay. In JavaScript, when you're referring to a class variable, it's this.grid. So if you've done any Python programming, this is like self.whatever in Python. It's going to hold the locations of the start location and the goal location of this particular instance of the search. So we have the starting X value, the starting Y value, the goal X value, and the goal y value, okay? It's also going to hold the cost. So the cost is going to be the solution cost. So in this case, every action is going to have a cost of 100, so it's going to be the sum of all of the actions. Next, we have this Boolean variable, which just says whether or not the search is currently in progress. This tells the GUI when the search has been completed or not. And essentially, all you have to do is when you're finished your search, you say this.inProgress equals false. Oops, I don't need this anymore. I'm going to delete that. So this.config is going to hold the actual strategy that you're using. This is just here to differentiate it from the solution code. You also have 3 other variables, okay? This is the path. So whenever you compute a solution path, you store it in this JavaScript array, okay? That's all this is for. You have the JavaScript array for the open list, and you have the JavaScript array for the closed list. So these are the data structures for the open list and the closed list of your search. All right. So the first thing that you have to implement is the start search function. This is pretty much done for you, okay? So in the GUI, whenever you click a starting location and a goal location, your search class, the start search function, is called. All right, that's what's called. And so it's called with the starting location, x, and the goal location, x and y. So what I do, I already have this done for you, okay? When you start a search, you say the search is in progress. So set this variable equal to true. Set this dot starting x, this dot goal x equal to the input variables that you passed in. And this dot path, we have to reset the path. Everything else that you should do in here to reset the search should be done in this function. So for example, just as a hint, one thing that you have to do is reset the open list. Okay, so you have to reset the open list when a new search starts. You also have to say this.open or this.closed equals this. Also, another bonus that you have to do when you start the search is you have to add a node of the start state to the open list. Okay, so those are the 3 things that you have to add to this function. Okay, there we go. Now, the second thing that you have to do is implement the isLegalAction function. So, again, like I said before, what is a legal action? A legal action is moving from one location to another location on the map. Okay? So, one second. Oh, that's the wrong spot. So you have x. The isLegalAction function takes in 3 parameters. It takes in an x and a y, and it takes in an action. And you know what? I actually have some slides that I can use to show you this a little bit better. One second. Should have showed this a little bit earlier. Okay. So here is a tile in the environment, right? Our environment, if we look at it from the start, it just looks like this. It's just grid cells, right? These grid cells have an x and a y value. X and y start at 0, 0 in the top left for this assignment, okay? So this is 0, 0. This is 1, 0 because it's over to the right by 1 in the x direction. This is 2, 0. This is 2, 1. This is 2, 2, etc. So that's how our grid works. These are how actions work. So if I am at a state x, y, in the environment, then I transition to other states via an action. An action is given, so any action is an X and a Y change. Okay? So, to move from this state to this state, I move up by 1 in the X direction, and I do not move at all in the Y direction. So the action 1, 0 is moving 1 in the X direction and 0 in the Y direction, and that happens to correspond to moving right. If I want to move up, then that's 0 in the X direction and -1 in the Y direction. Down is 0 and 1, left is -1, 0. Okie dokie. So, we're only doing up, down, left, and right. We'll be doing diagonals in the next assignment, okay? So that's how our grid works. So here in this function, it's a really simple function, okay? So this function should compute and return whether or not the given action is able to be performed from the given xy location. The arguments to this function, you have an x and a y. That's the x and y location of the position that you are currently at. And now also you have action, which is it's an array of size 2 containing 2 integers corresponding to the x and the y of the action. This is the action to be performed, representing the xy movement from this position. For example, 1, 0 is move 1 in the x direction and 0 in the y direction, meaning move right. For this assignment, the only action possibilities should be these 4 actions: moving right, moving down, moving left, and moving up. Okay? This function returns whether or not the given action is legal from the given location. So, what you have to do inside this function is 2 things. First, or actually 3 things. Compute the position you would be at by adding action 0 to x and action 1 to y. So for example, you can say let new x or next x equals x plus action 0. Let new y equals y plus action 1. Okay? So, then what we have to do, 2, check to see if that location is out of bounds or not. So how would we do that? Well, we can do something like this. If grid, or this dot grid, that gives us access to the grid, dot is OOB, right? So we have this dot, this dot grid. Remember, this is the grid, so we have the is OOB function. Okay, this dot grid dot is OOB nx ny. The grid also takes in a size function. That size is just going to be 1 for this assignment. So this means that the spot is out of bounds, so return false. Okay? Now, otherwise, if it's not out of bounds, then it's in bounds. So the third thing I have to check to see if nx, ny is the same color as xy. So what would I do there? I would say this dot grid dot get xy equals this dot grid dot get nx, ny. Okay? So that's how I check to see whether or not the grid at the current location is equal to the grid at the next location. And if it is, then I return true because I can legally move between grid positions of the same color. So I've essentially done this is legal action for you, but I just wanted to make sure that you understand how to use this, this function. Okie doke. Now, before I get into the meat of this, there's one other thing. I've given you a node class, okay? So again, remember from the notes, a node is not the same thing as a state. the node is going to contain the state and some other bookkeeping. All right? So here, the constructor of a node takes in an X, it takes in a Y, it takes in an action, and it takes in a parent node. So when you construct a node, you give it this.x, this.y, this.action, and this.parent. So, for example, the open list stores nodes. So if I'm in the start search function, I want to add the starting state to the open list, okay? So this is what you could do. You say this.open equals a new array, okay? So that's, you've reset the open list. And now you want to add a node there. So what you could do is say this.open. Now my syntax may be a little bit wrong. .push new node. And the node constructor takes in the x value. So this is going to be the starting node's x value, the starting node's y value. And then what else do we have? We have the action performed to generate this node, and we have the parent, okay? So the action here would be, well, we didn't actually do anything to generate this node, so we can just say it's 0, 0, okay? And the parent of this node is actually null, because the root node does not have a parent. All right, so that's what we do here, is that's how we generate the root node, okay? Perfect. Gonna delete that again. So now that we have that, here is where you're going to be spending most of the time on this assignment. It's the search iteration function. Okay. So let me just read this, and I'm going through all of it. This function performs one iteration of search, which is equivalent to everything inside the while true part of the algorithm pseudocode in the class notes. The only difference being that when a path is found, we set the internal path variable rather than return it from the function. When expanding the current node, you must use the this.isLegalAction function above. So what does that mean? Well, if I go back to the slides, in here, right, I gave you assignment 1 BFS, right? This is literally the solution to the assignment. But here's the big difference, okay? You are not writing this while loop. You are not writing the while loop. You are writing the contents of the while loop, okay? So inside the assignment, we have this search iteration function. That function is everything inside this while loop, okay? And we're dealing with the class variables of the search student function. Now, why is that? The reason we're doing that is because the while loop is implemented once every 60th of a second by the user interface. So the user interface is constantly calling your search iteration function, okay? So when I click here, a start node, and then I click a goal node, the first thing that happens is that it calls start search. And then it says, while the search.inProgress is equal to true, so while I'm still searching, keep calling that search iteration function. And the reason for that is because then we can do things like this, is that I can call your function one step at a time so that you can display in real time how your search iteration is actually performing, okay? Not only that, but I can do a single step of the algorithm at a time. And trust me, this architecture seems a little bit complicated, but when it comes to debugging your assignment, this is going to be an absolute godsend, okay? So I can actually click single step and step through the assignment in order to debug things. And so this sort of visual debugging is going to be absolutely insanely good for your assignment, okay? Now, go back here. Just talking about this function a bit more. If the search has been completed, so if you've found a path, or if the open list is empty, then this function should do nothing until the start search function has been called again. This function should correctly set the this.inProgress variable to false once the search has been completed, which is required for the GUI to function properly. This function should perform one iteration of breadth first search if the this.config.strategy variable is equal to BFS, or one iteration of the depth first search if the this.config.strategy equals DFS. There should only be a few lines of code difference between these search algorithms. So, here's a tip. You can use a JavaScript array to represent either a queue or a stack, okay? So, array.pushE pushes an element to the end of an array. If you use array.pop, you can use that to remove the last element of the array. So the last element of the array, that's a stack, right? So array.pop will make it act as a stack. If you use array.shift, then this will remove the first element of the array. So it will make the array act as a queue. So you could also use your own custom data structures if you want, but I recommend just starting and getting the assignment working just with a plain old JavaScript array, okay? And just to reiterate, this seems really complicated, but every assignment in the course uses this structure, so I won't have to go nearly this in-depth with every other assignment. All right, so here's the search iteration function, okay? First, we're gonna leave this here. So if the search, if not this.inProgress return. That means if the search doesn't have anything left to do, exit this function and do not do anything else, okay? Now, what I've done for you just as a demo is I've set up a dummy path to just be this dumb path that actually doesn't do anything. It just draws an L shape, okay? But what it does do is it shows you how to actually set the class variable of the path and return it, okay? So that's what this does. You have to delete all of this and replace it with the code for BFS or DFS. And here's how you'll do that. You'll say, if the config strategy is BFS, do the breadth first search stuff. If it's DFS, do the depth first search stuff. And the grad students have to do the ID DFS stuff, okay? And all this config.strategy, that's all handled by the user interface, so you don't have to worry about that. And so in this assignment, the cost is equal to the path length times 100. So you don't need to worry about the cost. I've put that code in there for you. And when you have found a path, and only when you've found the path, set this.inProgress equal to false. Okay? Yes, grad students have to do all three, but the first two are trivial, right? The only two other things you have to do for this assignment is the following. 1, a getOpen function. So in order to draw the open list and the closed list, we have to have a unified view of the open list and the closed list, right? So if I go back here and I look at the solution code, I have to be able to draw this red and I have to be able to draw this yellow. And so what you have to do for me, so all the slides and the VOD will be available, so you don't have to be paying attention right now. Don't worry about that. So in the getOpen, what I need is the following. This function returns the current open list states in a given format. This exists as a separate function because the open list used in search will store nodes instead of states and may have a custom data structure which is not an array. So this function has no arguments, and I want it to return an array of unique XY states that are currently in the open list. So all you have to do here is something like the following. For each node in the open list, well, first of all, I can do something like let open list states equal a new array. I'm going to say for each node in the open list states dot push and I'll push in node.x, node.y, and then return open list states. That's it. That's all this function does. Okay? And then the same thing down here. Now, get closed. If you just use the closed list as an array of states, then all you have to do is return this .closed. Okay? But if you use some other data structure for your closed lists, then you have to do the same thing here. So you'd say let closed list states equal a new array. Then for each node, or for each entry in closed list states dot push close dot x close dot y, or however you recommend. Okay, and then you'd return closed list state. So that's it. So that's what those two functions are. They are really easy, and trust me, the explanation for this. So this assignment is complex, but not complicated. Okay, so if all works, then you should have something that looks like this, where you click one thing and another, and it will generate the path between them. Okay, so that's the first assignment. When it comes to the second assignment, you'll already know all of that stuff, okay? And all you'll have to do is implement the new algorithm inside the search iteration function. So you have almost 2 weeks to implement that. I strongly suggest getting going on that as soon as possible, because as I said, it's complex but not complicated, right? Once you get into the flow of it, you'll say, oh, this is actually a really clever architecture. It helps me debug. And also for those who are really new to JavaScript, I recommend Chrome's debugger, and I'll just show you why. If I reload this page and I hit Control-Shift-J, it will open up the Chrome debugger, okay? The Chrome debugger has a console over here that you can use to print things to. So let me just show you one example of that. I have to erase all of the changes that I've made in here before I show you that. Okay, so what I want to do, just one second. I'm not getting into a JavaScript tutorial here, but just to show you that over here in my draw function, or let's see, whenever I click the toggle grid function, I can say console.log hello 3200. Okay? So console.log will print to the console. All right? So if I reload this and then I hit the toggle grid button, it will say hello 3200. Okay? So that's how you can debug using print statements in JavaScript. Also, there is a literal debugger inside Chrome. And Chrome has a really good debugger. You can use pretty much any browser for this assignment, but please test to see if it works in Chrome, because that's where we will be judging the assignment. The very last thing is that for every assignment, I have a bonus material, and the bonus material is that the top 3 students who get the fastest running solutions get an award on D2L and the street cred in class, and I will announce the names in class, okay? So part of this assignment is, once you get it working, try optimizing it on your own. We'll get into a bunch of optimization when it comes to assignment 2, but I want you to try optimizing assignment 1 first on your own, and the top 3 fastest solutions will get a little bit of a bonus. Now, I know I went way over there, but the good thing about online lectures is that you can just refer to this lecture whenever you want. All the slides will be posted for students, and you can look at this VOD. So I'm sorry it went a little bit long, but this actually gave us it gave us a lot more time to go over the assignment. So I just got a question. Is there a solution for IDDFS? So if you implement IDDFS correctly it has the same properties as breadth first search, okay? So when you select IDDFS and you click run tests, you should get the exact same results as your BFS. So that's how you know that you have coded iterative deepening depth first search correctly, is if it behaves the exact same way as breadth first search. And now, grad students, I only gave you IDDFS in the slides as a recursive function. So you are going to have to do some experimenting on your own. That's where the grad part of this course comes in. You are not going to be able to just look at the notes and copy my stuff. You actually have to turn that recursive function into the same iterative type of function that we've had here. Okay? So this is what's going to happen with every assignment. There's base functionality that everyone has to do, and then for 6980, there's going to be bonus stuff that the grad students have to go out and research on their own how to implement, and that's going to be a big part of their mark for the assignment. All right? So please ask any questions you want on D2L, but if the questions were D2L or email or Discord, if it was answered during this talk, I'm just going to refer you to the slides or during the recording. So this recording is long enough. I'm going to tune out here. I have another class in an hour and my voice is going to be completely gone. So thank you so much if you sticked it out the whole way. If not, I'm sure you're watching this for the assignment later on the video. So thanks a lot, and I'll see you on Tuesday.